All right, great. So thanks for coming to the presentation day, and great to see like most of you are here. And yeah, as I mentioned, today is the most interesting day of this subject, and hope all of you will enjoy it. All right. And before we started, I'll just mention something. The first one, it is very important that this presentation is peer review. So do make sure you download the peer review form from the assessment, from the Canvas assignment, and fill it and resubmit it. The deadline is tomorrow midnight. Then you can get your comments and your marking on it and upload it to the to Canvas before tomorrow midnight. All right, and just want to mention to you, the only marks we are getting averaging is the final mark or total mark, right? So which is the last item, right? So try to evaluate it as what you as what's in your opinion, and we will use the mark to get the marks for the others. All right, and also the peer review is only you are giving the marks for the other groups. Right, the groups other than your group. You don't have to mark on your group. All right, and also this is please make it serious, because I mean all the others marking are based on that, right? And yeah, that's the first thing. The second thing, I know there is a time push with some other subjects, advanced robotics and MMD. Then some of the students may not be able to stay here for the whole class. Then that's why I'm doing this recording, and then I will upload this recording to the Canvas. Then you can review it later and give the marks. All right, so if you can do that, that would be great. And also the deadline for submitting it is tomorrow midnight. All right, so as I mentioned before, peer review is very important to the others, and also it's a very good way that you can evaluate the works by yourself, right? So if by doing this, by marking on the other groups, by evaluating the other groups, then you will know what kind of a presentation and what kind of a project is a good one or not, right? That's a much efficient and effective way about understanding about this. All right, so that's the peer review. And what else? Okay, I changed the orders a little bit, but I mean, if you still requires changing of it, so just let me know. Okay, and yeah, another thing, I got a lot of requests about extending the final report deadline. So I've done it already. So please submit the final report by Monday, 31st. All right, and midnight, that's fine. And yeah, for the final report is per student, not per group. All right, it's per student. And you are requiring to write everything in the project. It's not only about what you've done yourself, but everything in the group. But you are free to share some kind of experimental results or figures, but don't just copy and paste the others. All right, write it by yourself, but if it's requiring some kind of figures or experiments things, then you can share about that. But you write it by yourself. Yeah, you also midnight, yeah, and yeah, what else? Yeah, so please submit everything through Canvas. All right, so everything through Canvas. All right, so any questions? All right, then if there's no, we can start. Yeah, so. Okay. It's fine, it's fine. The comments is mainly about yourself, but what we take is only about the marks you gave at the last. And you don't have to just averaging the 3 sessions, right? You don't have to do that. You just give the mark that you evaluate the project. Okay. And before we started, as I mentioned, because it's a hybrid one, it's very hard to manage. So what we'll do is you can see my screen there, right? And for each of the group, you are just sharing your screen and doing your presentation from your laptop, right? And for the students online, you just unmute yourself and you can speak, all right? And for the students here, then you need to mute both the mic and the speaker from your side and speak through my one. So my laptop will be here, always here. Good, because like if you are not doing that, then there will be a lot of echoes. You'll find this really bad. All right, so if all good, then we can start. And again, each group maximum 5 minutes is quite restricted. Otherwise, we can't finish it like within 3 hours, right? So each group 5 minutes, you can use the complete 5 minutes, or you can like speak. You can speak 4 minutes and have a 1 minute question and answer. Those are fine, but I mean maximum 5 minutes. And I'm just asking, is there any group who are doing live demo here? Okay, cool. You have, right? You're going to lab. You can, yeah, you can do that. Yeah, you can do it in the lab, and so U1 is here, right? Okay, so you have 3 extra minutes for each of the group, and if you want to do it in the lab, then probably you get another people who has a camera, and then do a like live stream or something like that. That would be great. And I mean, because you're doing live demo, so don't worry too much. If you find some issues when you run it, then don't worry. And then you can still debugging on that. And at the end of the presentation, you can do it again. All right, so as I mentioned, it's fully understandable about this. Okay, so if everything's fine, then we will start with group 4. Which project is self-proposed SLAM on Turtlebots. And the next group is group 8. Sure. Highlight.
Hello everyone. Our team project is a LAM Turtlebot. We aim to manipulate the Turtlebot into the random areas. It's use LAM to scan and build the map. My team's LAM technique will be based onto the leader. The result of these operations will return the map that we can use for many different purposes. The easy thing we have able to do is navigation. It's similar to what everyone learned in the mechatronics 2 subjects that make the robot follow the world. And our process have 5 steps. The first one, we set up the RS in Ubuntu, necessary hardware for coding and simulation. Next one, we set up the hardware to connect the Turtlebot. And then we make the code for navigation and SLAM. Then we apply this code to the Turtlebot. And the last one, we make the real demonstration.
For the simulation, we utilize Turtlebot package that are publicly available on the internet. Visual Studio Code is our IDE to interact with Gazebo and Alvis through ROS. Afterward, we construct a customized map for the Turtlebot to navigate in it. The idea is that the robot should follow the wall on the right of it and turn left whenever there's a wall in front of it.
Well, so our team project implementation is done on the simulations and physical hardware as well. So far, we are good with doing a simulation, and we also good with the bring up the Turtlebot so it can run randomly in the room. But however, dealing with the practical problem is a different story. When we start to building a real map, the material and the obstacle that we use is totally black. And you know that the 2D LiDAR is quite useless when it receives the light reflection from the black object. So that's why we quite fail into doing a remote. And we try to bring the Autobot into another room in UTS, but it's quite inconvenient because the process of bringing the Autobot is quite complicated. And also my Autobot need to be connected with the power by wires. We don't have battery for that. So can I say, I mean, to do a real demo, we need a small space for that. So in the lab, we just let the Autobot run randomly in the room, and we have no research for that. But I can show you like some research that we achieved from the simulation. Here we try to use we build a map on the Gazebo here, and then we use LAM package to run and draw the map on the Harvest. And then after we finish mapping, we will move on to the navigation by also using Harvest. But at this field, we cannot recording, just use the package from the other shop, and then just choose the place on the map, and robot can run anywhere you want. Yeah. So this is a little bit about the real demo, but the map is totally black, so that's why our LiDAR is quite, it cannot receive any information from the map. It just react with the yellow panel here, we can turn. So that's all for our LAM project.
Any questions? Yeah, I'm going to pick one. So which methods did you use for building the map and do the navigation?
The mesh to building
the
map.
Mapping, some other methods. You use some online packages.
Yes, the method. So we built the map as you see in Gazebo. So Gazebo allows us to construct a simple wall and obstacle like that. So yeah, we built the map
so you
in Gazebo.
Yeah. So like about the recording, we just try into LiDAR, the topic of LiDAR to receive.
Yeah, you use LiDAR. Yeah, to make yes. All right. So any other questions? All right. If no, let's send the group again. And next group is group 8, and the following one will be group 1. Okay, group 8, the online one. Group 8 project is about network.
So our project was using the Fetch robot to, we'll be running through the project aims, the challenges and the outcomes from the project. Sorry, my computer's running a bit slow. The main sort of project aim of ours was using the Fetch robot in ROS Simulator to pick up or identify and then pick up an object to be able to. So it was using the RGB sensor that's on the camera head, and the aim was to have multiple different objects so that it would be able to pick it up regardless of what object. The process we went through was installing the ROS and the Fetch simulator, which sounds like it's very easy, but that's probably the one we have the most difficulty with. Then setting up the environment with the ROS launch sensors, Sensors World Launch, loading the Fetch simulator into our environment, which we also had a lot of trouble with. Then we got into the sort of more technical aspects in terms of getting the sensors to identify the objects based on height, moving to grasp the object, and then being able to pick it up and set it down where we want it. So our environment setup was in ROS. We added 2 tables. Sorry, there's only one shown 2 tables and 3 objects, which was a tissue box, a soft drink can, and a bottle, just to have a variety of shapes. The robot camera has a range of 0.35 to 1.4 meters, which meant that we needed to set the table within that range to make sure it was within the workspace. So that all sounds very easy and straightforward, as shown by the image, but we ran into quite a few challenges, particularly with the simulator and the fact that it required Ubuntu 18.04, which unfortunately some of us had new computers that couldn't run Ubuntu due to the networking cards. So we only had one group member who could actually run the simulator. That was probably the biggest challenge we had. The second was a lot of the supporting documentation for the simulator was in Python. We understood the assignment was to be done in C++. We had a bit of difficulty in using the simulator and a lot of online resources because also none of us are experienced with Python. So we went quite far up until probably the mid-semester report trying to do this in C++ and then ended up pivoting and trying to do it in Python. Along with that, we also had a lot of debugging challenges just with computers crashing, the robot would disappear, the GitHub would deconnect, and then we had to start a new repo. It was a lot of fun. So this probably summarizes the majority. So there's just an example of us trying to load the robot. And I don't know if you can see, but the robot was very excited to be loaded. But eventually we were able to get it to load, and look, it's moving away from the table. Great. Very slowly. So at the end, where we got to with the project is that we were able to scan, we were able to scan the objects and identify based on height, and it would give us a list of objects, and you select which one out of the 3 using the interface that you want to pick up. And the robot would move to the object, doesn't actually pick it up yet, give me till midnight. But it would generally, at the point that it goes to pick up the object, crash. So that's where we got to with the project. Any questions?
Yeah. No, we kind of died.
Well, so we were initially planning to do the real robot. We were hoping to sort of have a working installation like a mid-sem before, but we just.
There was like 2 laptops that crashed. It was just Jess's one that was working, and then her repo crashed. So it took like 4 hours trying to git push, which didn't work, and then lost half of our code. And so there was a lot of
yeah. No, so we wanted to have a solid enough code to go near it. Yeah.
Thank you.
Yeah. Difference. Yeah. So that's what we.
We tried, and that's all that counts.
Yeah, we got an authentic experience through something.
I'm glad we all did it.
All right, cool. I think due to the time, let's send the curve again. The next group is group 1, and then followed by group 10. Okay, so then drop in because they have some other presentations in the other subject. One, and then here my team, right? Yes, everyone. No.
Okay. Uh, Alrighty. So we actually have the same project as the last group that came up spoke. Our project brief was essentially the same, just to pick up an object from a table, put it back down using visual sewing methodology. The requirements from our supervisor says we need to pick up at least 2 objects of different sizes and shapes and then deposit them safely at a predetermined location. We also had to successfully demonstrate the task in the gazebo simulation before we could test it on the real fetch robot. And our approach for the selected objects, we chose to use like a Rubik's Cube or something of a similar size and like a slim soft drink can, like a Red Bull or Coca-Cola can. And then code structure on like the highest level is essentially search objects in the table, calculate the end effector path and pick up the object, move it to its end location, and then check how many times the function's been run. If it's done it once, it'll go back and do it again. And then if it's done twice, it will finish and return to its starting pose. Yeah, pass on to Justin for the methodology.
So just the general structure of how the code works. It takes in the point cloud from the RGBD camera on the fetch robot, and it pretty much filters down the point cloud, so all the noise data is removed, and then it kind of separates the point cloud into different objects based on what is measured, and it clusters these different objects, specific objects, and then by setting particular boundaries, we're able to make the robot kind of like, hey, you only look for this object that's above the table, so above a certain height that we set, and then look for objects of this particular size. And that's how we're able to differentiate between different size objects, as well as how to get the pose and orientation of that particular object. And after the perception, we have the planning, which is the grasping of the objects.
Yeah, the perception for the node, it just takes in the fetch, the camera uses the fetch depth camera, and it just sees how much it has to translate to the object itself, and then we base it off of a move it function from the fetch website, the fetch robot website. We also implemented inverse kinematics to determine the motion and the for the robot to reach its desired position. And so if the arm was not to like detect or reach a desired object, it will go back to, it would retry again after a given amount of time, and then it will just be on a continuous loop until it finds it. Yeah, so now we're going to,
so this is what we were able to make. We had both the simulation and the real life robot. So on the left, you see the real life robot that we worked with, and the right is the simulation that we had. One of the troubles we had mostly was actually, it is laggy, but was actually when we were trying to implement in a real robot, we couldn't get the arm to move for a long time. And then turns out the emergency stop button was on, and it couldn't actually, use the arm. But we did have quite a lot of success in doing this. And here's just the left side. You can see top left is the point cloud compared to the RGB, as well as the bottom, just a couple of the terminal code with a bunch of instructions like searching for, it's calculating all of the manipulation path plan and what will be the correct kinematics in order to move the arm to that particular object and to the box. Yeah, you can also see that the placement and movement is not always perfect. In every single iteration run in the simulation and real life, the arm movements are always different because they're based on different inverse kinematic calculations. So it doesn't always place it perfectly, but we've managed to get it working, I think, most of the time. Yeah. Cool. So,
yeah, great. Thanks for sharing your it's very good move to. Just like you to share experience about what the difference is working in the simulator and move to the real world, and it may be useful for others.
Yeah, I guess the real robot has its own operating system. It's a lot more difficult to interact with. And then we encountered like certain issues with the real robot that didn't come up in the simulation. Like it wasn't able to, at some point, we think for calibration reasons, wasn't able to figure out its pose in the world, which led to it just picking up the object and then basically spinning around until you hit the stop button, which wasn't what we wanted.
Yeah, so one of the difficulties was the e-stop problem, and after that, when we were to put the same code, what it would do, it would detect the object, but it will move to the object and it would just either go way past the object or kind of like slam into the table. What we noticed is that it does detect objects, so it will move the object to different locations and it will go to that area, but then it will keep moving away from the table or like away from the object. And then what we realized we just had to cover it, which is something you didn't have to do in simulation because it's already covered for you. The reason why in the real life demonstration, because in the simulation, the robot actually turns to place the object in the spot. We couldn't actually get the robot to turn its base because when we try to calibrate the base, it just keeps giving us errors. We didn't have time to figure it out. Just to get at this stage took us about, or to get the robot to move the arm and pick up the object took us about 3 hours, 2 or 3 hours, just to get the robot moving. So it was a big shock.
Yeah, that's always the case when you're working on real robots.
Yeah.
So that's why we share about experience. All right, so due to the time, I think let's thank the group again. The next group is group 10, start to drop in, and after that there will be another drop in, which is group 19. Sorry about this, but I mean, after that there'll be no like drop in. All right, so group 10. We have a video. We have you can find strategy. If you really want, you can do that. No, we really probably could. You can use that.
Ready? Hi everyone. Today we'll be showing you our implementation of a test tube sorting robotic system using the Dobot robot and the Intel RealSense depth and RGB camera. Next slide. Okay, so within the medical world, it is common for blood or tissue samples to be mixed with chemicals in order to test them. The results of the test are shown through the change in color for the chemicals. So for example, a test for certain diseases, you might mix some blood with a reagent, and depending on the shade in which the liquid turns to, you'll know the result of the test. Now, this sounds straightforward enough when you only have to test a few samples, but what happens if you want to test 100 or 1,000 samples? Now, it's impractical to have staff constantly testing all of these samples all the time, and such an incredibly repetitive task provides a great opportunity for robotic automation. This is why we have designed a system capable of sorting multiple test tubes depending on the color and reporting this information back to the operator if necessary. Not only will this increase productivity as the robots can work 24/7 around the clock, it will reduce the error. Humans are very prone to making mistakes, especially when they're doing repetitive tasks. However, the opposite is true for robots. The more repetitive and straightforward the task, the easier it is for them to complete.
All right, so how it works, here we have a general guideline for the methodology of the system to allow for the DoBot to perform its function. We've listed as 8 steps, simple for people to follow to get the robot to do what we have programmed it to do. In summary though, the DoBot works in communication with the Intel RealSense camera to allow for its functionality. The camera works as a peripheral for the robot in understanding both the color of the hues and the location of the unique hue. And that information is communicated back to the DoBot to coordinate what order the test tubes need to be taken for the correct sequence to be created. Once this is done, the DoBot will continuously transport each test tube to the correct designated position until completion. We have a short video to demonstrate this.
There's a few potential modifications and improvements we can make to enhance our project. A key improvement you can see from the video is adding a test tube rack to deposit samples. This would create fixed positions for the DoBot to sort from, preventing spills or any further errors. Another modification that can be made is, rather than the DoBot being stationary, is adding linear rails to move the DoBot along the unsorted test tube rack, allowing for more test tubes to be sorted in one batch. And to further improve this, we could use a conveyor belt mechanism to deposit more samples and potentially increase the productivity of the robot.
Thanks for tuning in, everyone. We hope you enjoyed.
Okay, thanks a lot. Any questions? No.
All right, thank you.
So just within MATLAB, what we do is we would identify a certain amount of pixels on each test tube, because the important thing is that they began in a fixed location, which was pre-coded. So, using the pose of the camera and the pose of the test tubes, we'd just be able to identify the colors of each test tube using the camera, like just within the RGB matrix. Yeah.
Cool. Yeah. So just very quick question. What was the camera?
The camera was sort of behind the test tubes, if that makes sense, off to the side. I mean, it doesn't matter where you put the camera as long as it has a clear view of the test tubes. You just have to pre-code the pose of the camera relative to the base of the robot.
Yeah. That's my calling.
Very carefully, with a lot of tries, yeah. I'm not gonna lie, it was very hard to get the test tubes in the exact right location, because you need to know the pose from the beginning. We did want to implement, it doesn't matter where the test tubes begin, and the robot can detect where it is. However, we couldn't get that working in time, so we had to have a fixed location initially.
Yeah.
So yeah, just a lot of careful calibration.
A lot of drops.
Yeah. Oh, thank you.
Thank you. All right, so the next group is group 19, which is the very last one. And again, so this is the group 19, okay? Group 19.
Yeah. Right.
The group 19 project is a self-proposed. It's autonomous 3D mapping of an object using bus-free and real-science artificial.
Oh my god! Oh, not Linux. Yeah. I don't know if I'm sitting not Linux. Yeah.
That's a horrible thing.
Yeah, I think another thing.
Okay. So we'll go to the next. Next one is group 2. Group 2. Group 2 is about spectral point.
So our project was a set pulling the path of another robot. So we basically simulated the whole set of so to represent the guider, we used a robot waffle. And basically the waffle is controlled manually through keyboard input. And so our group was mainly focused on developing the algorithm for controlling the fetch by using a ROS package, which was basically a visual tracker. And based off the extract pose, we were able to control the fetch directly. So the camera video data is processed by visual tracker, which provides information to the algorithm, and yeah, that's controlled directly. So to set up the simulation, we had a gazebo map with a small office, and then we put furniture inside, and we had some obstacles and some like station equipment. So the market image, so to make the cube, we have the market image for the fractal. So we downloaded that, we placed it onto the cube, onto a cube model using Blender. And then that cube model was attached to the Turtlebot as a link component. We created a joint and it was connected to the base link of the Turtlebot. So that made the whole thing one solid model. And then all the models, including the fetch and the Turtlebot, were imported into Gazebo using a world file. So that was essentially read by Gazebo, and it sort of specified the location of all the components. And we also made a launch file for starting the world automatically and for starting several OS nodes, including the visual tracker and an algorithm. So yeah, that's pretty much how we did the simulation.
So next was image processing, where we just had to use a combination of the Fetch's RGB camera and also the VIS visual server platform. The combination of the RGB camera and this auto tracker allowed us to automatically identify QR codes, which are one of the most common identifiable features you run into in the modern day. This provided us with the XY coordinate within the camera frame and also the depth, which is the distance of the QR code away from the fetch. Next was implementing safety. So obviously there's obstacle avoidance, where we subscribe to the fetch's base scanner, which is a laser rangefinder. This provided 220 degrees worth of ranges and at a point through resolution. From this, you could determine whether an obstacle was to the left or the right, and then just turn the fetch in the opposite direction so that it could continue following a guide up.
So the core of this project is basically having an algorithm for path following. So in order to do that, the first thing to do is to sort of determine a target position. So in terms of the frame or the RGB camera of the fetch, how far away is the data that it sees? So to do that, I sort of restructured it from the top view, which is like a 2D grid. So using Pythagoras theorem, we can calculate the perpendicular distance, and then we can calculate the angle from the QR code in the fetch camera frame. And using these two information, which is distance and bearing, we're able to sort of have a target position. And then once we have a target position, what next? Next is basically a velocity control. And we decided to use a PID control. In terms of PID control, its really is that it has three components, which you have a proportional controller. It's a linear constant between your target position and your current position. You have an integral controller, which is basically address your steady state error, where when your error is infinitely small, then you sort of have to accumulate the error to be able to continue a viable PID control. And lastly, you have a derivative controller, which to prevent overshooting. For instance, when your guider is turning, but your fetch could be either not turning enough or turn too much, so it starts spinning 360. We had a lot of problem with that as overshooting. So basically to solve it, we basically just spent a lot of time fine-tuning this PID constants. And yeah, but in the end, we didn't use an integral controller because we never have steady state error, because the distance between the guider and the fetch is long enough that it will never reach steady state error. So that's it. And now we're just going to show you quickly a demo video.
So the fetch is reversing when it gets too close to the guider, and then it follows when it's too far away. And then the important part comes when the guide is turning, and that's where it's more likely to overshoot with the rotation of the fetch. So as you can see, it can follow the guide of both directions.
Yeah. Okay. And now it's a question.
Yes, that's pretty much it.
Yes.
Yes.
Do you have any issues when you have two pistons or switching from one place to the other place?
Did it any effects on your control?
On the beginning, it did. For instance, when the gather was spinning too fast, and then it was sort of catching this QR code, and then all of a sudden it catches the next one. But since we have a PID, it's always following that one.
And make sure the turtlebot didn't move too quickly.
We had put QR code on all faces because we thought that it might lose track, but at the end we just realized that because the PID control, it would never lose track of the current one.
Okay, so thanks a lot. Let's thank the group again. So the next one is group 19. Again, group 19. Okay. And the following one is group 3.
Yeah. So it's going to start with a little trial video kind of as a kind of
So probably I should go. So we developed. Yeah. So we developed an optimal scanning system using so we developed an autonomous 3D scanner
Initially, we planned to use like the UR3 and an IRB robot. The UR3 had an RGBD camera on it to scan the object, and then we were using another robot to manipulate the object. Unfortunately, we couldn't use the other object, so what we did was we manually manipulated an object around a sensor and then used the UR3 to generate scanning paths that would scan the object. So the system had adaptive camera positioning using the end effector of UR3. From that and the calibration of the camera, we could get the center point of the camera relative to the base and to where the object was located, just through some geometry calculations. Building upon that, we were able to develop a positional-driven point cloud stitching system. Initially, we had planned to use the iterative closest point method. However, for our application, the iterative closest point method, we found it had issues due to the lack of features, like large features. So stitching it through that method was a bit complicated. But then after we calibrated the camera, we were able to develop a really good manual manipulation based on the camera pose. And then from this, we were able to simulate the robot live on MATLAB, and then also send commands to the real robot, use a graphical user interface for camera positioning, and then point cloud captures, and then output this by combining the point clouds into an object. So we actually did this. This was us in the lab, moving the robot. So the robot will go across some scanning paths. It'll capture different angles, and then we will rotate that object manually. From here, we get an RGB point cloud. So it's got color and the point cloud positions. And then from there, so yeah, and then capturing the top as well to capture those top point clouds. And then from all of that, we were able to So this is a video of the exported point cloud. So as you can see, we've got multiple sides, and that's from the stitching, the manual stitching of getting those different sides and then combining it about the center. And that's all just using the poses and to generate, 3D objects, which was pretty cool. We didn't get originally we wanted to have a ply or an STL output. However, that was a bit difficult to implement in the end. The sizing, just didn't get around to it. Okay, that's the system.
We have time for the rest of the questions. Anyone? Okay, so I have a very quick one. So, how did you do this?
Yep, so I've got that up here. This. So this is our graphical user interface for the UR3. So that allows manipulation of that, and then we've also got a scanning menu. So here you've got a few different options. There's a manual scan, which is you set like the height and the position, and that captures a point cloud from that position. We've got a quick scan mode, which is just a basic right, left, middle, and top view. And then there's a detailed scan, and then there's the Yang mode. It's very complicated. And on this computer, I think it took about 20 minutes to run. So from this, we've set an object center. So this is done through the object depth here and the focus height. So if I click this home button, the robot will begin to move to that object depth and then the focus height. So the object depth, it's a little bit offset from the camera. So the like 0.75 is from the base of the robot to there. This also works in conjunction with the robot. We just add a little commands saying turning on the actual controller, and then that sends commands to the robot. From here, we can manipulate we want to pan in the positive direction, the camera will pan, and then it will also adjust its yaw value to align with the center of the object as well. So that's how we got the positional. And then from there, the point clouds, as we know, the end effector of the robot and the relation between the location of where the point cloud has been taken from, we can rotate the point cloud that we get from the object and start stitching it with the other collected point clouds.
Cool, that's great. So just mentioning, I have a 50 classmates who they're making this kind of program scanning using robots and also professional cameras.
Yeah.
Cool, thanks a lot. That sounds good again. Right, the next one is group 3 and following by group 5. And just want to mention group 3 is going to give a lockdown, right?
Hello, we have group 3. I'm Matt, Paulo, and Julian. And our project was the TurtleBot following the other TurtleBot. So a bit of introduction about it. Is our goals were mainly to be able to move the guide bot either manually or firstly and have the secondary follow bot actually fold around, and also using an IDP camera to be able to apply the feature. There was a second where that you see our little group one there actually use it to detect that blue square, and as well as be able to control it efficiently.
So to achieve that, so we had to control both TurtleBots. So for the guide, because that was the one which really didn't need a lot of image processing, so we could either do that manually through teleoperation. So we could either do it with a keyboard or a joystick, or we could do it autonomously as well with SLAM. That was also a possibility. And the follower, that was the one where we had to use the camera to do the feature extraction. So we used an RGB camera for that. So the main goal was to extract the images and then from those images get specific features that the TurtleBot could use to follow the other one. And then in doing that, also calculate the distances between the camera so that it sends the right velocity commands to the follow bot and then control the motors appropriately. So the feature extraction process, so it's a 4-step process. So we first had to collect the images, of course, from the camera, edit those images, do some image processing, so masking those images just to reduce the processing time, and also do centroid calculation so that you can get the distance from where the object is on the guide, and then the position of the camera and the feature on the guide. So to collect the image, we use the Intel RealSense. So those are some of the features of it. So you get the resolution at 1920 to 1080. So when you use the color setting, it's much slower when you use the depth setting. And then you also have the frame rate at 30 when you have the color image, and it's a bit more higher when you have the depth image because the quality is a lot less. So once those images are collected from the RealSense, it's just a matter of extracting those images. So if you're familiar with RAW, so whenever you launch the camera packages, so you get all those topics that essentially just store each image type. So if you want an RGB image, you subscribe to the RGB topic. If you want a depth image, you do the same. So once you have those images, the actual image processing that we use. So initially, we wanted to use OpenCV. So it's an open computer vision platform. It's widely used for image processing. So with OpenCV, it allows us to work with multiple image formats, and it also allowed us to mask the image. So in terms of actually reducing the processing time, it was a lot more effective. So initially, so we had either the choice of using OpenCV or MATLAB. So the main aim with both was to essentially just convert the images that we get from the camera to a different format where you could essentially just separate the luminosity of the image and the color information, so that regardless of how much light you have, you can still detect a specific color that you pick to follow as a feature. So in doing that, so once you actually have the proper image format, so what you do is you mask the image. So masking the image is more towards, as I explained before, just reducing processing time. So you essentially just want to have an image where you have the feature that you want to track and everything else is darkened, as you can see from the image there. But unfortunately, this was only applicable to OpenCV. We couldn't really get this done with MATLAB. And once you get the masked image, so you can see the little blob in the image. So essentially, that's just a Sanford calculation. So based on the feature that you actually extract from the masked image, you essentially just want to adjust the position of the turtle bot so that it knows where to go towards that feature. So that's where the Sanford comes in. So you can see at the top, that's the OpenCV implementation with the masked image. And then we also were able to do the same with MATLAB with the RGB image. And based on that, so you already have the Centroid, you essentially just send the velocities to the TurtleBot by just publishing it to the specific topic. And in controlling those velocities now is just a matter of like what type of controller you use. So ideally for this scenario, we wanted to use a PID controller. So essentially just calculating proportional integral and derivative errors, but we're only able to go with a proportional one, which introduced some error to the system. But with the image processing that was done, that was sort of like made up for the extra error that we couldn't ameliorate by using the integral and derivative components. So
yeah. And so then for our actual results, what we basically ended up going with was the operation for the guide. We were thinking we had some like slang stuff going. We thought the main thing for this one is just the follow-up bot. Like, can your follow-up actually follow the right one? So I was like, we shouldn't really spend too much time on working out the guide code too much. We really want to focus on the follow. Like if the follow works, that was kind of our entire goal. And then we ended up going with MATLAB rather than OpenCV, just because OpenCV really wasn't playing nice with some of the software we had. Honestly, the biggest that we can talk about now is like the challenges and stuff with just getting everything to work. The actual code itself was honestly not too bad. Like we did image recognition, all that kind of stuff. But just having everything play nice, we had a bunch of things we could probably talk for half an hour. But the main ones, OpenCV wasn't really playing nice with it, so we had to switch to MATLAB. And then all the error, because we couldn't quite get the PID working, so we just ended up with a proportional, which obviously has its own error because you haven't got any of the steady state error that I should talk about. And a stack more, but in general, this is what we ended up with our farming result. We filmed it just in case we did our code wouldn't work. But yeah, so you've just got the follow in front, one behind is just, as you can see, that's the MATLAB code of it's working out the center of that blue square and then adjusting its velocity of both motors to try and follow. Yeah. Next one. This one.
Understand that or come here to see the the thing is, do you want the online people to see it as well? Not really. Okay, I'll start switching on my camera as well. Yeah, for the online students, there is a lab demo here. Then if you can look through my video, then you can see the tutorials there. Yeah, I found that. Yeah, fine. That's very well. Always having this. Probably the majority is silent. You have to like initially make it separate. Yeah. Good. Yeah. Yeah. My favorite things. Oh, right. Oh, we're gonna have this one working because my data changed so that we don't have to update on this one. Yeah. How big is it? Yeah. Yeah. So basically, yeah. So it's trying to work out whether the circle is relative to the center. So the further it gets to the side, the more aggressive. But yeah, you have a higher the but yeah, it's deciding. It does for that's the proper camera. All right, cool. That's great. That's thanks to the group again for showing us the lab demo. And again, just want to mention the it's not working robot is the leader. It's not supposed to be like a robot. Right? The main work is about following the demo already. Right, so that's the second group again. Okay, so the next group is I.
So
okay, so we're doing the grasping control of the DoBot robot.
So the scope of our project was to identify the colored blocks on the board, to control the robot arm, and then to use these components together in order to move the blocks into their goal boxes. So what did this look like? So the RealSense camera creates a point cloud and then filters this down based on the RGB values and the XYZ coordinates. We can then do some calculations to filter out these RGB value points to determine where the blocks are in their clusters. We can then move the end effector to these coordinates, engage the suction cup, and move the blocks into their goals or disengaging the suction cup. So for the issues we encountered, as you can see from the footage, this system didn't always work as intended. The calculations for where the blocks existed in the 3D space was not always perfect. Issues were encountered early on, before more filtering and also redoing the maths for converting robot's coordinate system to the camera's coordinate system again. So reading the point cloud data. So occasionally getting red, green, and blue values from the points within the point cloud was an issue. In the next clip, you'll see us failing to get any values for any points that had red values that lay within the threshold we had set.
As you can see in the last clip, though, adding more light was a good way to solve this issue. It resulted in a more distinct determination of the red, green, and blue from each other. And this enabled us to find points more accurately that lay within a threshold. The RGBD cameras used for the 3D perception are particularly relevant for robots operating in unstructured dynamic environments, such as agriculture. In this example, of apple picking, the red pixels of the apples are separated from the leafy background, with each cluster then being fit to a predefined apple model. This technology is a welcome relief to Australian farmers who have recently been experiencing labour shortages and extreme weather, which have accelerated investment into ag-tech vehicles. These vehicles utilise the application of point cloud data to identify target fruit crops and then use this data to evaluate the ripeness, assess for disease, and eventually then harvest the fruit.
So throughout the project, we kept the position of the blocks fixed for the majority of our testing. This allowed us to confidently isolate each stage of the projects. For example, the DoBot arm control, the point cloud generation, color isolation, and pose and waypoint determination. But in the video, you can see that in the final stage of the video, we can throw the blocks at a random location, and the camera is able to calculate the position relative to the robots. And then using this position, we can control the DoBot to pick up the blocks. Okay. Yes, my computer is kind of laggy, so. Where's the menu?
Thanks a lot. Any questions? Any questions to do?
Yep. To the camera or the robot? Robot. Not really, because
we did a few times, like coordinating the arms.
Oh yeah, so the arm kind of sometimes want to go through the table, but it doesn't. So you just lift it up a bit, but you can stop it on time.
We also had one time where we had a failed test, but it just kept going.
Oh yeah, it's just like shaking on its own, even though the power supply's up.
That's so weird. It's so classic.
Okay, so one of the questions you mentioned about the
yeah.
Then have you like tried to evaluate the accuracy of that calibration?
No, we haven't like assessed how accurate it is. But we did have to redo it.
Yeah.
You come up to be off, right?
Yeah.
Cool. So if there's no other questions, let's ask the group again. Okay. So the next one is group 6. And the following one is group 7.
Got it.
Yeah, so I'm Marco. Sean. We're doing 3D reconstruction using RGBD camera and the EM sensor. So let me show you the result first. Yeah, so that's the final result that we got, the 3D reconstruct. So for the algorithm to convert the object from an image frame into a global frame, we're gonna convert from image frame to camera, then convert to EM sensor frame, then finally to global frame. So to generate point cloud, just simply use the triangulation, which we're gonna find the disparity to get the X and Y of the camera frame. Then the set is the RGBD data. It's simple. So after we generate the point cloud from image frame to camera frame, we need to get the pose of that point cloud. So how do you use? So that's why we need to use the EM sensor to get the pose. But before that, we need to calibrate the two sensors to get the relative pose. So before recording, we need to attach the EM sensor to the camera so they have a fixed pose. But at this moment, we don't know the pose of the camera. So to do that, we need to calibrate both sensors. So I use the ICP to get the fixed relative pose between two devices. So to do that, I get a checker box and place it on the EM sensor board. Then use a pen, which also attached to the EM sensor, and points to the feature points of the checkerboard and generate a feature points cloud in the EM sensor frame. Then I just I take a picture of that checkerbox and generate another feature points cloud, but in the camera frame. Then, if you're familiar with the ICP, so now I got the camera frame points cloud and the EM sensor frame points cloud. With the ICP, I will get the rotation and translation matrix. So this is the fixed relative pose between two sensors. So that's how I calibrate two devices. So then everything's easy. So then I just simply use the transformation matrix to convert the points cloud from camera frame into EM sensor frame and use it again from EM sensor frame with the EM sensor data to place it into the global frame. So that's the whole process of 3D reconstruction. So, so that's the ICP result here. All right, so for the result, if you look closer, see some of the points cloud, they are not aligned. The orientation is not aligned very well because there are some difficulties while I'm doing the 3D reconstruction because after doing the after performing the 3D reconstruction, not all the points are aligned accurately because it could be many reasons that I have to observe, but which I don't know. It could be the EM sensor, inconsistent data from the EM sensor, inconsistent data from the depth map. It could be when I'm recording, the EM sensor gonna move, and maybe I touch the EM sensor. So it could be many things which I have to observe and see and compare the difference between different results and see what's going on. So that is the most difficult and time-consuming part of I doing the 3D reconstruction. So yeah, that's all I guess. So any question? RGBD image. Oh yeah, sorry. So that is one of the RGBD image, and I convert it into a Google frame. Yeah, into 3D reconstruction. So
any questions?
That is all. That is the object. That is the example.
3D printed.
Yeah.
That's why it's me.
Yeah. So yeah.
It's for other projects.
Yeah. So because if you take a look at how others doing the 3D construction, like many of them struggling with after they do the 3D construction because there are many factors that affect the accuracy when you find the pose of that point cloud. Yeah. So.
Cool. I think, as I mentioned, it's a bit complicated project.
Yeah, there's a lot of mathematical issues.
It's
to
good,
be honest.
it's good to take it. Most of it is done at once. But I mean, for the calibration, and two senses, those are much easier way.
Yeah, I tried to use the hand-eye calibration, which is AX equals to XP. The result is terrible. I can't make it. Yeah, yes. Therefore, I decided to use the ICP.
Yeah, use the ICP one.
Yeah.
Just one thing is probably your ICP result is not that fault.
Yeah, I think so.
I'm not aligned. That's why you don't.
Yeah, I tried a lot of ICP from different resources, like from other open resource, and I kind of not sure what's the critical point that makes the accuracy.
Yeah. One of the things that
okay.
Yeah. You want to do it.
Yeah, I want to do it. Yeah.
Okay, cool. You want to
yeah, that's an easy way to do it. The more accurate one is AX equal to XP, the hand-eye calibration. It's more accurate.
I mean, but
the hand-eye calibration.
What I mentioned is, so you have two sets. You have the correspondences.
Yeah.
And then it's much easier.
Oh.
Yeah. Okay, so here's the time. Let's cleanse the curve again. The next one is curve 7. It is also a very complicated and fun project.
Especially the lack of clarity of what.
All right, so today we'll be presenting our assignment on 3D control and path planning for surgical robotic catheter in the aorta based on ultrasound. So a bit of background information about what that all means. A catheter is an extremely thin tube that is inserted into a major artery at the groin or wrist. It is fed through until it reaches the designated valve or artery. In this case, the designated location is the aorta valve, which is one of 4 main valves that control the blood flow in the heart. The catheter can have a multitude of applications with different parts and devices added to the end of the catheter. Some of these applications include blood sampling, closing holes in the heart or repairing defects, opening narrowed heart valves, or removing plaque buildup. In order to get the desired location in the aorta, cardiovascular imagery is used. The ultrasound camera provides a live feed of the catheter traveling through the artery. This imagery will be explored in today's presentation. For the project, we were given the Phantom Experiments dataset. This dataset contains ultrasound images from the catheter while traveling along the path with the aorta valve. As seen in these images, there is a defining characteristic observed in traveling the aorta. On the right image there, this is called this irregular shape. This is the irregular shaped lumen or aortic wall, and will be the feature that will determine the new path running the catheter. The catheter should be directed along a path that is through the center of the aortic valve to ensure there is no collision with the lumen. Another data set that is important when determining the new path is the EM scans, taken from an external machine that determines how far the catheter has traveled within the aorta. We are able to process the EM scan data to plot the location of the catheter at the time that each image was taken. To find the center point of the lumen, we first need to process the images for ease of use to get rid of any unnecessary data and noise. First, the image is converted to grayscale so that it is defined by a singular layered matrix that can be easily manipulated. In this grayscale format, each pixel has an intensity value between 0 being completely black and 255 being white. The values between the maximum and minimum are obviously shades of gray. The image is then masked to eliminate any pixel with an intensity below 150 by setting it to 0. From there, a white circle is drawn around the ultrasound frame to assist in approximating the center point, scenarios where the lumen goes outside the camera frame.
So to find the inner ring of the masked image's lumen, a quadrant approach is taken. This involves plotting points just outside the camera center point, that middle white circle you can see there, and having those points travel outwards until they find an intensity. This method of detection proved to be accurate. However, some strange results were observed when the lumen's regular shape sat outside of the camera's field of view. After the code has searched in all 4 quadrants of the image and located the lumen, a minimum and maximum point was determined for both the X and Y coordinates and only the previously plotted points. Maximum and minimum in the X and Y axes are then used to make 2 intersecting lines, and a line intersection function was then used to output an X and Y coordinate that much more accurately represented the center of the lumen. Due to the shifting shape of the lumen as the catheter travels along its original path, as well as some minor outlier values, not all center points are 100% accurate. However, they do offer a far better and safer path planning trajectory of the catheter than allowing it to frequently encounter the aortic walls and reacting accordingly. To help demonstrate the data processing and path planning capabilities of the project, we implemented a GUI. This GUI displays the raw unprocessed image, processed image, and the image with the plotted center point. It then outputs some rough control figures using the degrees of rotation the catheter will need to undergo to direct its bend axis towards the new center point path, as well as the bending amplitude to be applied to the catheter's sheath. This control methodology of rotation and sheath bending is standard amongst surgical catheters. And although we don't have any physical hardware or simulations to test our outputs, these values should be able to be calibrated and mapped to a robotic surgical catheter control interface for future testing and tuning. That's basically the project. Any questions?
Probably about 1 or 2. The first thing is you try to get the center point of that ring, like the inner. Yes. By getting the maximum of the point. Yeah. The intersection. Have you ever facing the ring that is not fully observed?
Yes, we have seen that, and that additional external white circle we added does help offset those, because without that, it was just shooting values off into nowhere and causing us some grief. We did actually find a rather interesting study that basically investigated exactly this, that had some much fancier methodology for estimating the wall path outside of the camera shot. It was something that was sort of outside of our scope. Yeah.
Another one is, can you explain a little bit in detail about what are the 2 parameters that you're showing, which is related to the control of the catheter?
Yeah, so the surgical robotic catheters, the way that they're maneuvered manually or automatically is that they've got a specialized sheath that can be manipulated to actually bend the tip of the catheter to help navigate it around bends in the aorta or in the veins, arteries. And so our goal was to basically rotate our catheter to the point where its bend axis will actually tilt the tip towards the center point, which it may cause a little bit of weirdness at first, but over the span of the artery, it should help give a relatively good guidance.
All right, cool. There's no other questions left than the other group again. All right, the next one is group 9 and followed by group 11. 9?
Hello, we're online.
Oh, cool. Yeah, and you can share.
Hey. Yep, I share my screen. Okay.
Yep. So we'll just start. Hi, everyone. So our group did group project 7, Turtlebots following each other. Our team members include Elma, Shaya, and myself. Next slide, please. So some of the main targets we set ourselves to fulfill were to complete the program using image processing implemented on a follower Turtlebot, use a unique pattern design that can be implemented behind the guided Turtlebot, allowed the program to successfully work in an office or corridor or lab environment where it would face obstacles while trying to maintain a certain distance from the guided Turtlebot, and make sure to use the onboard camera to complete image processing techniques learned from the subject. Next slide. The MATLAB script that we made contains 4 main functions. These work hand in hand to successfully establish a connection between ROS and MATLAB. So it identifies the pattern and moves the robot. The 4 functions were the Turtlebot task function, process image basic function, process image advanced function, and the calculate movement function. Now I'll get my other members to tell us a bit about of a summary for their functions.
Shane, we can't hear you. We can't hear you.
Can you hear me now?
Yeah, all good now.
Okay, sweet. Okay, so I'll start from the beginning again. So my role was to work on the ROS communication and the MATLAB communication between each other. So a quick overview of how we got this to work was we used the resources that was provided in Canvas, also some further research. We started off with using ROS shutdown on the code, which actually gets rid of any interferences that may be running in the background. Second, we had to check the IP address on the virtual machine so we can use that to communicate with the MATLAB on our computer. We then also subscribe different aspects of the robot to different nodes while ensuring that we only have 10 messages coming in to avoid any overfill in the buffer. Using ROS Publisher, we sent out the data to the robot. And also what we did, we also set parameters. Some of these parameters were actually inspired from a MATLAB example from a website, from their website actually, which required some tuning for us to achieve some smoothness for this project. For the smoothness of the robot, we actually added in a P controller. We did not use integral and derivative because due to some limitations and input lags we were facing. In general, talking about difficulties, probably one of the most frustrating tasks for me in particular was installing Ubuntu. Our tutor said that we had to use a separate boot for it. And unfortunately, my MacBook doesn't support that. So at the end, I used VirtualBox, which is a free software for Mac, to run the Ubuntu. And being with the group that we have, we all actually started using a virtual machine. So yeah, that's, I'll pass it on to Jason, I believe, to next PowerPoint.
That's me.
Oh, okay, sorry, my bad.
So the image processing of our project, we've split it up into 2 modes. So we have the basic mode, which is actually using color detection. So it makes use of the LAB thresholding. So depending on which color we have, we've tuned the thresholder to find a color in that range and obviously detect it and locate it within the camera view. So you can see its little GIF, sorry. It's actually tracking the blue circle at the moment. Now with the advanced mode, we make use of matching surf features. So we fed the program this King of Hearts card. And what it's actually doing is it's looking for this pattern and trying to recognize it within the camera view. And once it's done that, it tries to find the sensor position of this pattern and give out the X and Y coordinates within the frame. So you can see that GIF here where it's tracking the pattern. So I'll go next.
How the calculate movement function basically works is once a pattern is identified, controls for the angular and linear velocities keep the pattern centered. The distance set to maintain from the guided turtlebot is 0.5 meters. If the pattern can't be seen, it will rotate for 5 seconds. And the calculated angular or linear velocities, if they are higher than the one set, it'll just clamp it at the maximum to reduce any errors. The image on the right now displays the turtlebot detecting the pattern and moving to center it and stay a safe distance away from it. Next slide. So collision detection and avoidance was included using the onboard LiDAR sensor. This detects any immediate collisions. It has a plus minus 45 degrees. Sorry. It has a plus minus 45 degrees tunnel vision from the front. When an object is less than 0.35 meters away from it, it basically shuts down the velocity while trying to keep track of the pattern. This is shown in the images as it stops moving due to the wall and then just watches the pattern. Next slide. So this is a little bit of a demo of our project.
Sorry, this is our little demo. So we've got the GUI here to start and stop the program. You can see we're running a virtual machine that's running the gazebo simulation. We have a simulated world which has 5 turtlebots, 4 of which have specialized markers, and 1 is simply just following those markers. And that's it. You can see it's going under the table, going around. So we're actually controlling that guider turtlebot with the marker using the teleop keyboard, which is in one of the turtlebot packages. And that's it. Thank you.
Any
Thanks
questions?
a lot for your work. And due to the time issue, then we're going to move to the next group. Let's enter group again.
Yep.
Next group is group 11 and followed by group 12. Group 11 is turbo following each other. Second one.
Yeah, so we were actually doing the same project as the last group. We basically had what called so the scheduler project basically included creating our own selected one, a unique marker. So we needed to have recognizable features that would be able to detect and needs to be placed on the back of the robot. I really went with the equal time. And we also had to do image processing. So obviously taking the feed of the camera and capturing the marker and then processing the position of that marker in the raw frame. And finally, the control of the robot. So once we had the position, we then had to control our following robot to actually follow the other one. Okay, so that method was to first read the ROS messages. So we use MATLAB to read these messages. That's just a topic graph of the real robot. So that was riddle 1. I don't know why it's changing. We basically have to subscribe to the ROS messages. So we subscribe to the robots, ODOM, the RGB, and the depth. Then to refine the RGB image. So this is an example of the image that we would have got. We've made it grayscale, and then we've actually refined it to get rid of any of the gray values so that we could just focus on the darker values. So we used a threshold of 10 for the simulation, but we had to really increase that for the real robots because real life is different. So then once we did that, we were able to detect the marker using read equal markers as a function on MATLAB. And we were able to determine the central point, which we then also determined on the depth image. So we could get the 3D pose. And then finally, once we had the marker detected and the pose generated, we would use a G controller to determine the velocity that we needed to publish to the following robot, to the command velocity, in order to control. Okay.
For the hardware we're using is the Turtlebot 3 Waffle with the Intel RealSense camera R200, which has RGB and RGBD. And for the DCB and the Turtlebot 3 Waffle is the OpenCR and the Intel Duo. For the software we're using, it's GitHub and MATLAB 2022A. Being MATLAB is our main programming language. And we're using ROS, either melodic or noetic, and Linux Ubuntu 18.04 with gazebo simulation as well. So for the hardware challenges, our main hardware challenges is that there wasn't enough servobots in the locker that we were given, although we could work with only one of them for the forward turtlebot. And there were also missing parts for the turtlebot we did get, which is the LiDAR, but we didn't end up using it, so it was fine. And not all the turtlebots were working. Some of them couldn't even load Ubuntu or were just really inconsistent. And for the software and code, it was a bit of a learning curve for our group being unexperienced with ROS and Ubuntu. Working together on the same code through GitHub with conflicts between the local codes was a real struggle. Getting the turtlebot folder to detect turning in general was really difficult for our group. And there was movement oscillations during following and mismatch of camera resolution for the RGB and the camera.
This is a video of our simulation within Gazebo. So within Gazebo, we get the ROS node loaded up in MATLAB, and we basically can publish and subscribe the velocity and the image from Gazebo's simulation. The simulation image is quite different to what happens in real life, but basically this is how we were debugging. And as you can see, it can move forward and backwards, and it can do a little bit of turning, but we had some trouble trying to get it to turn around. So this is the code for the main velocity controlling part of the program. We basically have like a 5-minute timer of how long it'll take until it stops following the little robot. So it basically controls it via detecting whether the marker is moving forward or if it's rotating. If it's rotating, it just basically waits until it's moved away from its rotating spot and goes to its previous location and tries to find a marker again. Or if it's just moving forwards, it will just move forward and move backwards with it. But in the end, we only got it to do the translating option. This is our real life demo. Another challenge we had was the depth image that we got from the camera in real life was a different resolution to what we had in our simulation. Basically, you have to correlate the point in the RGB image to the depth camera. So whenever it tries to grab the depth cloud, it didn't really match up to what was in the RGB image. So if it was like a smaller image, I think it was
they were
like,
the same. Yeah, they were the same ratio. So
same ratio,
we
yeah.
just had to go about the differences and just into that. So it's just slightly smaller. It's the same ratio. So it's a pretty easy fix in the end. Yeah.
Very cool. So let's thank the group again. Next one is group 12 and followed by group 13. So group 12 is self-posed project. It's about internal processing using UR3. No, it's that. What is that? Yeah, probably touch interesting.
So I wonder if it's here. Put it as an option somewhere. Does you open up the video? Yeah. You open up now? The option. Is there an optimized video somewhere? So incorrect. There. There. Great.
The goal of our project is to have a robotic arm serve a ping pong ball of a specific color set by the user. The user will place The goal of our project is to have a robotic arm serve a ping pong ball of a specific color set by the user. The user will place two balls in a random X, Y, Z location within the set workspace and select a color for the UR3 to serve. The project uses an RGB camera to locate the static ball using color detection for object recognition, centroid tracking, and depth map analysis. Once the location is determined, the data is translated onto real-world coordinates. The UR3 uses the location to determine the appropriate joint angles to reach and hit the ping pong ball. All CAD models were designed on SolidWorks and Blender. The workspace in which the balls are to be placed are indicated by triangular etching on the desk. This workspace was determined by using the field of view from the data sheet of the D435i RealSense camera and trigonometry. Furthermore, for accurate calculations of depth, all balls are placed at a minimum of 28 centimeters away from the camera, as according to the data sheet. The UR3 simulation can successfully approach the ball and serve, as shown. To simulate the UR3, the team utilizes Peter Cork's robotic toolbox in MATLAB.
The camera can successfully implement object detection and centroid tracking. The color of the ball is identified and its centroid is obtained. The process of obtaining the color is by specifically selecting the first dimension of the RGB matrix. Then, using a median filter to remove noise, the image is transformed into a binary black and white image. Through the process of area opening, we can remove objects that have fewer than 300 pixels and recreate a new black and white image. Then, measuring the properties of the image regions, the XY centroid can be calculated. The centroid coordinates from the RGB are then projected onto the depth map. Using the coordinates, the distance of the object from the ball can be accurately recorded. Then the XY pixels coordinates are projected onto the real-world coordinates using the following equations. A demonstration of the RealSense function is shown. The program loads the simulated environment, matches the simulated UR3 to the real one, and prompts to the user to choose an option. Hit red, hit blue, or finish the program. As shown in the RealSense camera can detect either colors.
By returning the XYZ values using the getLocation function under the camera class, we can now know the location of the ball in the Cartesian space and thus use inverse kinematics for the UR3 to achieve the joint angles necessary for the UR3 to move towards the ball as calculated. We use a series of intelligent waypoints to greatly lessen the chance of a self-collision by the UR3 and its long racket end effector, while also getting warned about undesirable robot movement by seeing it execute on the simulation first. As can be seen, the UR3 successfully moves towards the ball both in the simulation and in the real-world demonstration. The initial end effector transform is given a small offset to the ball, and it just simply rotates to hit the ball after. We keep the program looping so that different ball locations can be tested easy, and so that the user can select Finish to send the UR3 back to its resting joint state, just a quality of life feature. We're Ball Gazers, and thanks for listening.
So we can do a live demo of the camera function and as well of the UR3 simulation, but they can't work in conjunction right now because the situation isn't really ideal. So I don't know if we have enough time for a demo.
Yeah, sure.
We can do questions and answers.
No, I mean, do the live demo first. It's the most important, interesting part.
Yeah, let's do it.
The map kind of gets confused and everything gets blurred into one image. So we can try. So the camera has a function in the class called getLocation, and usually the UR3 object will just call that function to get the real-world code.
I'll mute from my phone. You need to be second.
You guys can't really see this clearly, but there's a GUI that asks you for red or blue. This GUI will continue to loop, so you can keep choosing in between red or blue as you wish. It's a bit difficult to see, but it'll pop up again once it goes to the red ball. And then you can choose blue, random, and it just keeps going. Yeah, sorry guys, couldn't see that properly.
Alright. But cool. It's a wonderful project. Any questions? Any questions? I'm very quick ones here. So you use a RGB camera, very sensitive, and use some way to do like right? Yeah. I saw it.
Yeah,
That's why you do the
no, so that wasn't really to do the calibration. That was just to measure how accurate we're getting. Yeah. So
you're having the same issue the other group was having.
Yeah.
Why, right?
So our depth is fairly accurate. The issue is the camera's not calibrated. It's not a factory calibration. It's taking in the intrinsic relation between the quite wrong. So even when we use the equation, we're off by 4 to 10 centimeters consistently.
Yeah.
So we just have to account for that as well.
Yeah. Okay, so no questions, that's it. All right, so the following one is the table.
We're online.
Oh, cool. Yeah, so feel free to share your screen and start.
Yeah. Is that showing? Yep.
Yeah, all good.
All good, yep. Good afternoon. We're group 6. Our project is Turtlebot following a straight line by observing a square. Our group members are Daniel, who worked on the vehicle movement and kinematic analysis, and Anupa and I, Kalpa, who worked on camera calibration, sensor reading, and the data extraction from the RViz module.
The main aim of this project was to program the Turtlebot to follow a straight line, whilst manipulating its movements using the information obtained from an onboard sensor. The robot had to observe all 4 corners of a square object and drive in a straight line, which was perpendicular to the object. The Turtlebot 3 simulator was utilized to design the simulation environment and interact with the robot. To achieve this, first Ubuntu 18.04 was installed onto a virtual machine, and VMware Workstation Pro 16 was used to run this operating system. ROS was then installed, which allowed us to use the Gazebo simulation framework. Next. The key engineering problem for this project was to effectively program the Turtlebot to perform the following tasks. So the first one was to utilize its onboard sensors to map the environment directly ahead of the robot. Second was to observe all the 4 corners of the square object, which were located directly in front of the Turtlebot. This was relative to the Turtlebot's coordinate frame. And then third was to manipulate the drive functions of the Turtlebot to enable it to travel in a straight line, which was perpendicular to the square object. So this is our project timeframe. As you can see, week 2 to 3 was spent forming the project proposal and clarifying design specifications. 3 to 5, we started looking into the simulation environment. 5 to 9 was spent working on the code to manipulate the robot's movement. And then finally, 9 to 11, we analyzed the 3D visualization data.
Yep. Once we had the movement and camera module sorted, we followed this design methodology. By performing our image calibration and gathering our data, we using the RViz module, we could then poll that data to perform feature recognition on the environment. And using this, we can determine where it is relative to the square and where the final location is. We then use the alignment module to reduce the offset between the robot's perpendicular position and its rotation. And then we follow this 3-step method to rotate the robot parallel to the square, drive forward until it's intersecting the center line, and then rotate 90 degrees to face the square, so it's facing its location. After the alignment is within the tolerance, the robot simply needed to move forward until its set distance is reached.
So the code we used comprised of 2 nodes, the camera interpreter, which was then publishing data to the motor control node, which upon receiving the data would then figure out how to get to the perpendicular line by using the gradient intercept of the 2 points to then turn towards it, drive the set distance 90 degrees, and then continue on until it reaches the desired distance from the object. Overall, this produced fairly accurate results. We were able to get within our tolerances reasonable consistency. And on the next slide here, we have a video demonstrating our results. And when it loads, you can see the system that we designed of how it's, apologies. Yeah, so it finds the object, figures out the perpendicular line, drives perpendicularly towards it, and then tends to face the object. Which happens just about now.
Yep, this project was a great opportunity to understand the importance of our teamwork and time management, and provided a great learning opportunity regarding 3D image visualization, 2D and 3D sensors, ROS programming, which we weren't familiar with, as well as the RViz module, which we weren't familiar with. And future utilization of the ROS program can be used to develop more advanced projects and develop more, by following more online tutorials, we can develop our knowledge on the Turtlebot and its programming. Thank you.
Ooh, thank you. Any questions? Yeah, I probably have two very quick ones. One is which is the perpendicular line? Can you show it again? Which is the perpendicular, like the path or trajectory that you want the robot to go?
If we go back to the video, I think we only got about halfway through, but we can see more clearly how the robot functions. It was driving, turn, and then drive forward until it reached 5 meters away from the object.
Mm-hmm. Yeah, sure. Another quick question is like, how did you detect the square and also the angles with respect to the square?
The plan was that we would look at the 4 corners of the square, and then using that we could figure out where it was relative to the camera's frame, and also its orientation, given that we knew the size of the object. This would then be turned just into the position and the rotation, which would be sent to the motor control node.
Yeah, okay, cool. Thanks a lot. Let's dance the group again. So the next one is group 14. Group 14 and followed by group 15. All right, so both the two groups are controlling question for the Dubai robot. Yeah. Or you want to play the video with so probably I'll just explain this. I mute from your side. And also the speaker. Or the speaker and the mic.
Gotcha. This is the control and grasping for the DoBot robot for the group project for sensors and control for mechatronic systems, and I am accompanied by my teammates Miriam and Richie. The main idea of this project was the integration of the Intel RealSense 435i and to utilize its capabilities of reading depth-colored images and transfer the data collected from the camera to control the DoBot for specific tasks. We set out the DoBot to perform a task to determine ripe tomatoes from unripe tomatoes, which was exemplified by using red blocks and green blocks to replace the ripe tomatoes and unripe tomatoes respectively. The DoBot was to extract the data from the camera and see which tomatoes are which and organize the different colors by placing them on opposite sides. By setting out these goals, we were able to move on with the project by first calibrating the Intel camera by using the checkerboard method to gather the data for determining the focal length as well as the principal points in the camera. We ran the calibration twice to achieve the smallest pixel error possible to collect a more accurate database for the positions of the blocks that the camera will read to transfer the data to the DoBot for more accurate movements. From there, we fixated the camera to a bird's eye view as seen by exercising our extreme engineering brains where the camera is looking down to the blocks and take a photo using ROS.
So using the image processing toolbox, we take the photo taken by the camera, turn it into grayscale. Then we use a certain threshold value to turn it into a binary image. Then we use infill to fill up any holes. Then we use BW label to label the image and turn that binary image into blobs. So as you can see here, the binary image and the blobs are labeled from 1, 2, 3, 4, 5, 6. We then use region props on the binary image to determine the perimeter, area, and centroid of each of these blobs. Now, here's just where we extract the centroids of the blobs that was found with region props. And then from these centroids, they're plotted onto the original image as seen here.
The colors of the blocks were also obtained by comparing each RGB value with each other, where 1 would equal to red and 2 would equal to green, and that's how we separated them. Once the centroids have been calculated, we then convert the pixel coordinates from the image into a frame of reference to guide the movements of the DoBot, where we are able to position the DoBot end effector to roughly where we want it to be, which is on top of the blocks for the suction cup end effector to activate and pick up. We do this by taking the camera parameters as calculated previously from the calibration and moving the image origin to the principal point in reference to the block centroids, and calculate the block's respective X and Y coordinate values in reference to its Z value from the height of the fixed camera position, where we're able to interpolate between the 2 coordinate frames to move the DoBot. The camera to DoBot conversion was in reverse, as in the X coordinate frame of the camera was the Y coordinate frame for the DoBot, so we had to reverse the order of the matrix for the DoBot to move to the top of the centroid of each block, where the X coordinate is now the Y, and vice versa. We did have some contingencies and errors between runs, given the nature of the DoBot, where sometimes the end position of the robot to stack the blocks on top or move to a specific location was not consistent and different each time. The one recorded shows the DoBot stacking the blocks on top of each other by extracting the color data of each block to transfer them to their respective locations in the frame. But as you can see, the DoBot would sometimes drop the block from a height or turn off the suction cup completely. This is an error with our code, as we wanted to give some tolerance to the DoBot to stack the blocks in case it crushes the block below, and the end effector activation was very volatile when testing. Overall, we are happy with what we were able to achieve with our system. However, it can be more efficient and effective by having consistent runs between tests, as well as implementing visual servoing, where we are able to dynamically visualize the blocks in a moving frame instead of a static fixed position.
Cool. That's all. 5 minutes video already, then just a very quick question if you have.
Yep.
Yeah, so when we were taking the photo initially, we found that just fixating like our camera lights in between to take the photo just achieved a better result, more accurate one. We tested it twice where before we implemented the lights, the centroids of what we calculated from the center of the block were just completely off. So yeah, implementing those lights just gave us a little more accurate data set.
Cool, then let's thanks the group again. Cool. 1 second. Yes, the next one is group 15. 15?
Yeah, we're online.
Oh, cool, cool, cool. So feel free to share.
Oh, sorry. Yep, just give me 1 second. You guys see that?
Yeah, all good.
Okay. Yep, Hong, it's all up to you.
Hi everyone. Today we'll be talking about project number 3, control grasping for Dubot robot, and our team have 3 members, Liam, June, and me. Let's go to the introduction. Our group is working on the project to create some algorithm to sort the color object into separate container. To do this, we need to do image processing, color detection, and pose handler. About the code structure, next please. About the code structure, to do this project, we use MATLAB and ROS. We need to set up the camera and ROS launch it in ROS to start image processing with MATLAB to detect the object and its position. Then detect its color if there is any required color object. After that, it will be a pose handler, which is to calculate Dubot and effector pose and object pose to see if it is able to grasp the object. When Dubot pose has moved to the right spot, it will activate the pump to grab the object using the suction head and move it into the container. Next please. About the camera for color detection, we use the Intel RealSense RGBD camera. From this camera, we can calculate the position of the object in the camera by depth image and identify the color of the object by RGBD image. As you can see, some example on the slide is extracted red object from red layer of RGB image and cancel all the color from green layer and blue layer, and we will get the black and white image to show up the white area for detected object, and the center of the white area will be where the suction head should touch. However, in initial method we use only like 3 layers of the RGB image, so it's not really accurate. So we came up with the new solution, the better solution of masking and detect the most intense color position of the object. And Liam will talk more detail about this.
Yep, so like Hong said, we masked off anything that was too light or too dark for each color, and we combine them to increase the accuracy. So as we can see here, there's red containers here, and then these are the greens. Unfortunately, we didn't have any blue items to test. So we can see here, the greens and the reds show up. Yeah, we also remove any, I guess, smaller specks / pixels detected, and we just filter them out. So we can still see some here, but yeah, it should have gotten rid of most of them. We can also see that after the color, we determine the object center based off the intensity of the color. So there were two red color objects here, and I guess this was determined to be the most red object. Unfortunately, this was heavily affected by lighting and background interference, so that's why we have a white background in the back. I just used the Dubot container lid. Yeah, and then so this led on to visual servoing. So we had 2 options for visual servoing, which was eye to hand and eye in hand. So we ended up using eye to hand because we had problems mounting the camera to the Dubot, and in the end it was just easier. So from the color detection code, we could determine the distance from the camera to the object, and then from there we could determine the object's distance from the end effector, and then move the end effector to the location right above the object, and we would just lower the arm, collect the item, and move it to the container. The container's location was hard-coded, so we just collect the item and then just move it to a set location. We have a quick demo here. Oh, I'll just skip to halfway because it's just initiating the DoBot. Yeah, so I put pause functions in between just to make sure it would function properly. Yep. Next, and yeah, so difficulties faced. First off, just the DoBot driver installation wasn't that clear online. It took us quite a while just to get that installed. And the next was the color detection. So it was heavily affected by lighting and the background. So we had to just use a white background pretty much. I'll try to like cover up most of the background. And then the end effector to object calculation. So for some reason, the calculations we had, it would move the arm outside its limits. So it would actually, I guess, jam the robot. So we had to constantly restart it and just redo the calculations. And like I said, camera mounting. So we just ended up doing eye to hand. And then finally, the DoBot end effector command was not working with MATLAB. So there is a command on with the drivers where we can just change the end effector's location, but that wouldn't work. So we had to convert the end effector location to a joint, to the joint like parameters, the QLims basically. That's pretty much it. Thank you for listening.
Yeah, cool. Thanks a lot. Since you've already used 6 minutes, and just very one quick question if you have.
Sorry, I can't hear you.
You can't? Okay. Yeah, I think it's more than 6 minutes already. Then maybe we can move to the next one.
Yep.
Thank you. That sounds good again. Yeah. The next group is group 16, which is video serving with monitoring camera.
Okay, so hi, visual serving a handheld monocular camera. So, a high-level requirements for our project was to get communication between the USB camera and MATLAB, to recognize a distinct pattern from the camera, recognize the position and the movement of that set pattern, determine whether or not, determine the direction of the pattern from the origin point, and track that pattern from that origin. Then have the ability to display that pattern, display the directions to an operator that will either pan the camera or rotate the camera. Okay, so this is our basic flowchart of how we did our code. First, we initialized ROS. Next, we generated a base image. So to do that, we just held the pattern pretty much flat towards the camera, perpendicular. And from that, we initialized figures, and then we started to get into our loop. So for our loop, what we did was we constantly pulled the image from the camera, took that image, and we put into our first function called boxFind. In boxFind, pretty much what we did was detect the checkerboard pattern, and from that, find the corners of that checkerboard. And with that, we found our region of interest. The reason why we picked a region of interest is we'll come in later to region of interest. We just found that there. Within boxFind as well, from the corners, we were able to find these lines. I'm not sure you can see very well. There's a blue line for our vertical positions, and then a red line for our horizontal. So with these lines, we took we took these lengths of these lines, and we took them into our next function of rotation detect. And pretty much what that did was find the length of these two lines compared to each other. So what we found out is, if you tilt your pattern one side close to the other, visually, this line will be longer than this line. So we looked at that value and we just said, pretty much get that to 0. Next, we took the, well, we did pretty much do it for vertical and horizontal. Next, we took translation. Now, with translation, we took the corners that we found in box line, got the average position of that, which gave us the center, and we found found the center position of our baseline image and the center of our translation image. We just pretty much drew a vector from those two centers. Okay, I believe that covers everything. So we're just going to, sorry, I forgot one last thing, Z-axis rotation. So this was probably the most difficult part, mainly because I was including surf. Now, the reason why it was difficult is because surf had trouble detecting our pictures in that pattern. As you can see, the pattern in this image is quite simple. We tried making it more complex by drawing random shapes and lines to help surf find features. But in the end, it was still quite tricky. So that was probably one of the most the unreliable part of our project. This is Z-axis rotation. Otherwise, everything else went quite spectacular. So now, I'm just going to do a quick demo for it now. Got a minute. It was still not long to So that's our raw image. So using ROS, we used the node, the USB cam image raw. So normally we wouldn't have this up, but for the sake of the demonstration, we'll keep it up. So having that there. And so you can see it immediately starts off with the translation. Yeah. Immediately starts with the translation vector, and all the other ones will then also appear up there. So if we get, okay, normally this would have enlarged so that it would fit the window, but it doesn't want to this time. But you can see that if Marcus holds up the board directly to the center, if he can. So if he moves it to off of the camera. So if I move the camera up and to the right, the translation vector also moves it to the right. If I move it to the left, top left, the translation vector will follow. Bottom left, left as well, bottom right, there you go. So that's how the translation vector works. It's taking the origin and it's comparing it each time. So now when we do the X-Y axis of rotation, if I were to center it as well as I can, center it, and I rotate forward, it will move so that it's as if I'm moving the camera forward in the X-Y rotation. Moving it backwards generates the same thing, moves down. Okay, now if I move it according to the horizontal, now I'm shifting the camera to right. So yeah, then same thing for the other way. Now for this part here, for the Z-axis rotation, this is probably where we have the most difficulty because as you know, when it comes to rotation, there it took a while, but about there. So when it comes to rotation, you plus 180 and you'll get the same sort of rotation. So Marcus is now moving the board slowly. You can see that it likes to jump all over the place because Surf is constantly updating it. But normally, let's rotate more. Let me rotate some. So this should be as perfect as we get it. If we rotate it slightly, you can see that the Z-axis rotation rotates with it. Yeah. Jump. That is basically all of it. And then here you can see, oops, yeah, that basically ends it. So the other thing that we would like to do is that we tried our best to optimize it because we realized that when we first did this, as you can see, the total time it took to display all of this took 4 seconds. So you get 1 frame per second. It's too slow. So when we optimize this, I think it's overheating now. But when we do this without screen sharing, we can get it smaller, 0.48 or 0.52. So that brings me to the end of the demo. Any questions?
Any questions? Yes, it seems like you've done everything I expected from projects, but using a different method. But it's great you have a new research method compared to what you learned, right? Yeah. So and also it's great you can calculate this three different angles of rotation. That's in the 3D space. There are three like different angles of balance. Yeah. So probably the rotation dropped a lot is because you use the catwalk, and then you rotate it by pi, then
it looks exactly the same. So yeah, that would have been one of the modifications we would have done because we noticed it today, but we could have used things like QR code. There were like other prints that we could do that like more distinct shapes. But the point that we remember that it was just like, oh, do we really want to risk it? Yeah.
All right, so I'll process the group again. The next one is 17. This is working on sort of a flowing picture. 17, yeah.
Good afternoon, guys. I'm Doug. We got Remy and you. We're Group 17. We did the group project, the corridor by following one another. We're on to our key objectives that we kind of based off what we're given were to generate a 3D office environment on Gazebo. We're then going to use a RGB camera to detect the marker of the which will be placed on our leader robot. We'll then develop a code to follow the guide in the environment. And then we'll implement a collision and detection program using the LiDAR sensor, and then create a demo video to show like kind of what we've done as a whole. So for the environment creation, we just created like a pretty simple one, like you can see it up here. Just got like a corridor down the middle and tables on either side, so we can just navigate through different obstacles. This was all created through a simple like world file that was drawing from the Turtlebot Gazebo. Like it had a dependency linked to that. With this, we had to ensure that the spacing between the two robots was right for the RGBD camera, because we found that if it was too far away, and we'll speak to it later, it struggles to detect the features of it. And I'll hand over to Remy for the next one.
Yeah, so for this step, we did the image processing for the feature detection. We used the Turtlebot Waffle which had the RGBD and the camera. The marker QR code, we did it through Blender and we input it through and place it right behind the guider. So it's attached to it and it will move with the guider. And just the general process of our image detection code is that we use the surf feature method because it had really fast commutation and was very good for real life application, and it's good of getting the feature points while it's moving around the environment. We'll get the features from both the image in our file and the camera image from the Turtlebot, and we'll try to match these features and find points that align with each other. And these generate a lot of points, but most of these points are quite accurate because they are looking at edges. And to get a more accurate reading, we will get the inlier points, and we'll use the depth camera to find the 3D location of these points on the marker.
For the following strategy, once we've collected the matched points and the depth values, we can calculate the mean location of those points in the camera frame. So we can calculate the centroid of those features. And we use triangulation to calculate the X and Y of the camera frame, so we can tell where the light is located. We can calculate the angle of rotation, and thus we can rotate towards the QR. Then we can generate a point that is a certain distance behind the guider, which was the intersection point. And then we could move to that point and check if it has reached
So some issues and problems that we encountered was that just finding a optimal distance between the Turtlebot and the Guider robot. We found that if the Guider bot was too close, the depth image would just be like mostly dark in this image right here. And if it was dark, it will return us some NaN readings. And once we get that, we'll just get issues with calculating the position, and it will just continue moving without stopping. It was the same thing with the feature detection code as well. If it was too far away, it could not detect any features. So find the right spot between 0.5 and 0.9 meters away from the Guider was what we found the best. Also some visual issue with the RGB camera. It was a bit dark in some areas, so we had to adjust the image and brighten it up. And lastly, just some turning issues. We weren't able to turn the Turtlebot at large angles. We had to slowly turn the Guider bot and let the Turtlebot rotate before moving. So it was a lot of moving and stopping, getting the right, waiting for it to turn and move straight. And yeah, I'll pass it on to Doug.
Yeah, and then so just some future works that we'll implement moving forward would be to implement a PID controller to help smooth out that movement, and that'll hopefully alleviate some of those problems we were having with the turning. We'd also like to trial it with actual hardware to see how the difference goes with like interfacing with hardware versus running it through the Zebo. And then another one that I would like to touch on once they potentially develop a more robust search feature. So currently, when our follower loses the QR marker, it just stops and starts to rotate. It doesn't actually really actively search for it. So if we were to maybe try implement something where it's like almost mapping out using the LiDAR and starts actively searching for where that leader robot might be. It's just a little video of what we had done.
Yeah, so it's just on the bottom right, it just shows that it's always constantly getting the features being detected, and once it's detected, it's moving towards the intersection point from the marker. And we're trying to we are manually controlling the Guider robot using the keyboard through the terminal. So then we just try turning around and just moving across the environment. Yeah.
Let's go one quick question. I have a very quick one. So you mentioned like the cockpit rotation from the next vision.
Yeah, so once we've collected the match features, we got the points, got a collection of all the points and the depths are used. Then we used the mean to calculate the average point that we've collected and the average depth. Then we put it together to create one single point on the box of the QR. Yeah. And we use that point and the average depth to calculate an angle.
Okay, cool. So thanks a lot. So that's the deal again. Then the very last one is group 18. It's group 18 on here. Group 18 is group 18 here online. Now it's group 18. Oh. Group 18. No. Group 18 once. Yeah, so the group. Yeah, I'm going to check the names. Group 18. Stone, Tim, and Bok. Probably they are online because seems like they are Vietnamese names. Probably they are not here, right? Okay, then probably I'll mark it as missing, then we'll do something later. Oh, that's the thing. Yeah, that's the problem. No? No group 18? All right, then I'll contact the group a little bit later. And I'll try to find a way that you can do a peer review. So probably if they can submit a video about their presentation, then I can share it to you. Okay. Yeah, let's do it by tomorrow. I'll contact you if there's something changed. Right? Yeah. Oh, you can submit it here if you want. You can submit now if you want. Yeah, sure. Okay, so I think we've done all the presentations, and just want to have some conclusions or suggestions about the presentation. I think you know about what I'm saying, why it's doing this peer review, right? For the presentation, it is, and then I believe now you feel like you can understand much better about what a presentation is a good one and what a project is a good one, right? And how to present your project in a good way. Right? So those are something I want you to understand and have a better feeling about it. And some suggestions on the presentation. I think all of you have these feelings now, but I'll just give some conclusions. One is for a robotics project, so the live demo is always a better way to persuade the others, right? Comparing to a video demo. And a video demo is better than a simulation. Right? A simulation is better than just pictures. I think all of you have the feeling now. Then probably that is the way that you, if you need to present your work later, this is something that you can consider. And another thing is about, I saw lots of groups you mentioned about challenges, right, in your work. But I mean, mention challenges is a good way that you show the others you've done all the work, right? But don't mention it too much. That's the thing. So your main work is your main work. Your main work is always the most important thing other than the challenges, right? So if you want to like present your challenges, try to make it in a minimal way. Right? Do not make it as a main part of the presentation. For example, it's a 5-minute presentation, and I think some of the groups present in 1 minute about challenges. Then probably you can spend more time on the main part and also the experiments and the demo, right? And another thing is about the timing. I did it in a gentle way, so I didn't stop you in any of the presentations, but I definitely seen some other cases that the chair directly stopped you, and you will feel really, really bad. Trust me, you will feel really, really bad. So timing is also very important. So for example, if later, if you present something, they ask you to present it within 10 minutes, then try to within 10 minutes. Otherwise, the chair will stop you at 10. Then you are missing lots of like very important parts in your presentation. And you will feel really, trust me, you will feel really bad in that way. So that's why I'm not doing that in the presentation. Okay, so I think that is something I want to like give some suggestions about presentation, and some things in the following. One thing is if you finish your project already, then you need to return the equipment or the sensors back to the mechatronics lab. That's one thing. And also the peer review, as I mentioned, is very, very important. And we are taking your peer review as the marks of all the other groups. And yeah, so I'm going to upload this video recording as soon as possible. Then if you didn't do it, I mean, if you're missing some of the presentations because of the other subjects, then you can have a look and give the marks. And yeah, and also about the video and code submission. So the deadline is today midnight. Yeah, so please submit it via Canvas. And also the final report, I've already extended the deadline to the coming Monday, midnight, right? So try to submit it. And also I've sent you some structures already. So try to write it as complete as possible. And at last, it's time to say goodbye now. The last one is not about now, it's time to say goodbye. So just some final words. It's my true honor to give the lectures in this semester, and just so all of you are working very hard on the lectures and tutorials, and also the group project. And I just want to say thank you for all your efforts, for all the parts of these subjects. And as I mentioned before, so I will be really, really happy if you can use some of the things that you learned from this project into your future career. That will be like the great thing that I have, right? And thank you so much. We will have some transition time next week, the week after next week, and for the families. I'm sorry to say that's the very end of this. I have 3 transition times, and feel free to come to me or join in Zoom. Right. Okay. Yeah. Oh, that's SLS. Yeah, probably like you can save it as an old version. So, all right. Yeah, thanks a lot. Thanks a lot. Like, yeah. Thank you. Yeah, just fine. Just fine. Yeah. Thank you. Thank you, guys. 18, group 18.